Measurement risk and decision rules in the context of ISO 17025. Hello, Oliver Power here from NSAI's National Metrology Laboratory with a short presentation dealing with measurement risk and the decision rules used when making statements of conformity based on measurement data. When it comes to ensuring the competence of their operation and the reliability of the results that they produce, ISO 17025 is the golden standard to which all calibration and testing laboratories aspire. In the most recent revision of this standard, clauses were added which require the laboratory to take measurement risk into account when making statements of conformity. In particular, they must adopt a decision rule which describes how measurement uncertainty is dealt with when making such statements. This short presentation uses Microsoft Excel to explain some of the important ideas underlying measurement risk and decision rules. So let's imagine that we wish to make a conformity statement based on these acceptance limits here. That is, the object or system being tested has a certain property, and if the quantity value of that property lies between 95 and 105 units, then we deem it acceptable and denote it as a pass. If the value is less than 95 or greater than 105, we denote this as a fail. For reasons of clarity, let's concentrate on the upper acceptance limit. Here is the measurement scale. And the red arrow indicates the upper limit. Values below this limit constitute a pass, while values above constitute a fail. To test whether the test object or system passes or fails, we must measure it. And let's suppose that our expanded measurement uncertainty is plus or minus 1 unit. In line with normal practice, the expanded measurement uncertainty is given with a coverage probability of 95%. This green arrow represents an interval of plus or minus 1 unit. So if our measured value is, say, 102, and our expanded uncertainty is plus or minus 1, then we believe there's a 95% probability that the true value of the measured quantity lies in this green region here. Now it's very important to understand that the measurement uncertainty has been derived from a probability density function. That's PDF for short. The PDF gives us the full picture of the distribution of possible values of the quantity that we have measured. So if our measured value was 102 and the expanded measurement uncertainty was plus or minus 1, then this blue curve shows the PDF from which the measurement uncertainty has been extracted. The PDF provides us with a full description of the information we have about the measured quantity as a result of making the measurement. It shows how the possible values that we could attribute to the measured quantity are distributed. 95% of the area underneath the PDF curve lies in the range shown by the green arrow. So there's a 95% probability that the true value lies between 101 and 103. 2.5% of the area under the curve lies above 103. So there's a 2.5% probability that the true value is greater than 103. Similarly, there is a probability of 2.5% that the value is less than 101. Now obviously a reading of 102 will be designated as a pass, but we can ask, based on our result, what is the probability that the true value is outside the acceptance limit? This is the same as asking, what area under the curve lies beyond 105? In this case, the area is clearly 0. So there is 0 probability that the true value is outside specification. There is 0 risk that we have made the incorrect statement of conformity. We say that the false accept risk is 0 in this case. How about if our measured value was 103? Well, the width of the PDF doesn't change because our measurement uncertainty is the same. But the PDF does shift along the measurement scale in the direction of the acceptance limit. But again, the area above the limit of 105 is 0, so our false accept risk remains at 0. How about if our measured value was 104? We would still judge this to be a pass, but now the PDF overlaps the specification limit. 2.5% of the area under the PDF curve lies above 105. So there is a 2.5% chance that the true value of the measured quantity is greater than the acceptance limit. There is a 2.5% probability that the measured object or system fails. So we now have a 2.5% false accept risk. If our measured value was 104.5, which we would still judge as a pass, but now the proportion of the area above the acceptance limit has increased to 16%. So the false accept risk has increased to 16%. If our measured value falls right on the limit of 105, and we judge the result to be a pass, then clearly we incur a false accept risk of 50%. There's a 50% chance that our decision is incorrect. We might equally well judge a result that falls right on the limit as a fail, but since 50% of the area under the PDF curve lies below 105, there's a 50% chance that the true value is within specification. But we've judged it as a fail. In this case, we say we have a false reject risk of 50%. A measured value of 105.5 would also be judged as a fail, but because 16% of the PDF area falls inside the limit, there's a false reject risk of 16% associated with our decision, and so on. We can see, therefore, that due to the measurement uncertainty, there are ranges of measured values on either side of the acceptance limit where there is a significant false accept or false reject risk. What we mean by significant is a risk greater than 2.5%. The orange arrows represent these zones of risk. If our measured value falls anywhere within these zones, and we make a decision based on the result, there is a significant risk that our decision will be incorrect. In this range of values here, our false accept risk can be anywhere between 2.5 and 50%. And we have a similar false reject risk for values in this region here. The purpose of a decision rule is to state clearly what attitude is taken to measured values in these zones of risk when it comes to making a statement of conformity. There are several approaches to take. One is to ignore the existence of these regions entirely and accept that sometimes, when the measurement result lies close to the acceptance limits, our statement of conformity based on the measurement result will have a significant risk of being incorrect. The most conservative decision rule is to judge any result that falls in the orange region as a fail. Our range of acceptable values, which was 95 to 105, has now shrunk to 96 to 104. The good news, however, is that our false accept risk is never greater than 2.5%. You can see this when the measured value is 104, which is at the very upper limit of our new acceptance zone. Then only 2.5% of the area under the PDF lies above the actual acceptance limit of 105. The downside of this conservative decision rule is that the false reject risk can be as high as 95%. A third approach is to state that any measured values that fall within these orange ranges are judged to be a conditional pass or a conditional fail. So we now have 4 regions. Up to 104 is a pass, between 104 and 105 is a conditional pass, between 105 and 106 a conditional fail, and above 106 is a fail. Yet another approach is to introduce a guard band, as is shown here. Notice that we have shifted the acceptance limit from 105 to 104.5. This equates to introducing a guard band of 0.5 units, which in this case is 1/2 of the expanded uncertainty of measurement. Now we judge any value that exceeds 104.5 as a fail. As you can see, a reading of 104.5, which sits right on the new guard banded limit, corresponds to a false accept risk of 16%. And this is the maximum false accept risk that we can have using this guard band. So the effect of the guard band is to reduce the false accept risk. And you are at liberty to choose whatever guard band that you deem appropriate for your situation. You will recognize that the conservative decision rule that we discussed previously corresponds to a guard band whose magnitude equals the expanded measurement uncertainty. The final decision rule I will mention is that you can introduce conditional pass and conditional fail zones based on the guard band. In the conditional pass zone, the false accept risk is between 16 and 50%, and in the conditional fail zone, the false reject risk is between 16 and 50%. In summary, we can say that the existence of measurement uncertainty results in false accept and false reject risks associated with any statement of conformity that is made based on the measurement result. There are ranges of values on either side of the acceptance limits where these risks are significant. The bigger the uncertainty, the wider are these ranges. So first of all, it is of the utmost importance that there is a reliable estimate of the measurement uncertainty. Then a decision rule can be used to state how results that fall in these zones are dealt with from the point of view of conformity statements. I should mention that this presentation has dealt with specific false accept and false reject risks. That is, the risks associated with the conformity statement based on a particular measurement result. You can also estimate the global false accept and false reject risks, which you can think of as the risks associated with a conformity statement based on any reading from a measurement system. But that's for another day. If you would like to read more on this topic, please see Guideline G8 produced by the International Laboratory Accreditation Cooperation, or this Eurochem guide. Thanks for your attention.